This is Chapter 21, Part 2, Electric Circuits. We're going to learn about series and parallel circuits, and we'll learn about the different advantages and disadvantages that each one has. In this first diagram, we can see there's a battery, a 24-volt battery, and it's connected in parallel to 4 resistors. Now, we'll learn what that means, and we'll learn what the effects are in this video.
Series circuits. One simple way to arrange components in an electrical circuit is to create one large continuous loop with the components. So let's say we have 2 batteries and we connect those to some wires and a switch, connect those to a light bulb, connect that to a resistor, and then finish the circuit. This is a series circuit. Batteries in series. When batteries are connected in series, their voltages add up, but the total current is the same as each individual cell's current. So here we have some C batteries. It's a very common size. You probably used them before. And C batteries, each cell is 1.5 volts. Now what happens if you line them up like this is you increase the voltage. And so you keep adding. Each battery adds its voltage to the whole, and so we have 4.5 volts since we have 3 units of 1.5. However, whatever current the batteries produce is going to be the same as the current that one single battery produces. And that brings us to basic circuit principle number 1. Each element connected in series has the same current, or amount of charge, as any other element in the series circuit. But the voltage of the power source is the sum of each series element's voltage. Alright, so here is a simple series circuit. We have 2 12-volt batteries in series, and so that'll be a total voltage of 24 volts. And we have 3 light bulbs. Each of the light bulbs has a resistance of 10 ohms. And we see the flow of electrons. All the light bulbs have the same resistance and same brightness. Notice what happens if I interrupt the circuit. Since this is a series circuit, and if I split the junction, everything goes off. Everything goes off. This is the disadvantage of series circuits. So let's reconnect that there. All right, so I have these 3 light bulbs, and let's get some values here on our voltmeter. If I measure the overall voltage of the battery is 24, just as expected, 12 plus 12. Now let's see what happens to the voltage as the current passes through each light bulb or each resistor, because you can consider the light bulb a resistor since it has a resistance. Okay, so let's measure up here what happens. All right, well, if I connect this, okay, so it says 8 volts. That means there is a voltage drop of 8 volts when the current passes through that first bulb. Now if I measure the voltage of this next bulb, it's also a voltage drop of 8 volts. And of the third bulb, just as you would think, it's a voltage drop of 8 volts. And so what I have here is all the electrons flowing through with a current that's equal through each of the bulbs. But I have a voltage drop of 8 volts through each resistor. And so notice what happens here. The electrons come out of the batteries with 24 volts, but then it drops 8, and then another 8, and another 8, which goes back to 0 to repeat the cycle again. Another neat thing to look at is the following. I'm going to remove the voltmeter for now. Okay, now let's suppose that I change the resistance of one of these bulbs. Alright, so let's do it for this guy here on the left. I'm going to change the resistance to, let's say, 30 ohms. And let's see what happens. Interesting. What happens is the 30 ohm bulb burns brighter than the others. Why do you think that is? Well, it's kind of a cool thing. Since you know that the current's the same throughout, the only thing that can change is going to be the voltage. And so what happens is this high resistance bulb sucks up more of the voltage than the other two can because they're following Ohm's law. Now let's see how that works. There's going to be an overall voltage drop of 24 volts. We know that because the electrons come out with 24 volts, they have to drop back down to 0 before the cycle continues. But let's see how much voltage each one of these bulbs absorbs. Okay, so let's measure the first one. All right, in the first one, there's a voltage drop of 4.8 volts. In the next one, there's a voltage drop of 4.8 volts. But in the third one, the high resistance one, there's a voltage drop of 14.4 volts. So we can see that a lot more voltage is being used by this high resistance bulb, simply because V equals IR, and so if the R goes up, the V has to go up, right? And if Ohm's law is true, then there must be a direct relationship between voltage and resistance. If voltage goes up, resistance goes up, and vice versa. That's exactly what we see happening here. Therefore, the high resistance bulb burns the brightest because it absorbs more voltage than the other two do. Capacitors in series. Connecting capacitors in series is like using a capacitor with a large distance between plates. Alright, remember how when we were talking about capacitance, we had this formula over here that's on the right part of the screen, C equals K EOA over D. And we learned that capacitance increases if you have larger plates, so area A is bigger, but capacitance decreases if you have a larger distance between the plates. And so if you have a bunch of capacitors in series, the effect is similar to increasing the distance d, or using a capacitor with a large distance d, you're going to get a smaller capacitance. And sure enough, what happens when you connect capacitors in series is you're decreasing the overall capacitance, or CEC, equivalent capacitance of the circuit. Capacitors connected in series do not have the same voltage across them, but they do all carry the same charge. The voltage of the power source equals the sum of the voltages across each capacitor. Resistors in series. So let's say that you are connecting resistors in series. Well, that's a lot like using a long resistor. Alright, remember when we talked about resistance, we said that R resistance equals rho L over A, where rho is the resistivity, L is the length of the resistor, and A is the cross-sectional area. Well, we can see that if you have two resistors in a row, that's really very similar. It's just like using one long resistor. And so we can talk about Rec, or equivalent resistance, and that would be here in diagram B. The equivalent resistance would be just like having one long resistor. And obviously the lengths aren't drawn to scale here, but the behavior is the same. If you have two resistors in a row, it's like having a long one. And that's kind of how to make sense of why when you're dealing with resistors, you really just add them up if they're wired in series. You add up the resistances of each resistor to get the total resistance. Now, resistors connected in series can be replaced by a single equivalent resistance without changing the current in the circuit. The current I is the same throughout, and the voltages V1, V2, and V3 add up to the voltage of the power source, epsilon. Alright, so you often see batteries labeled with an epsilon, and all that really stands for is an abbreviation, EMF. And EMF is electromotive force. Now, I don't like to use the term that much myself because I think sometimes it confuses students. It's really not a force. It's not measured in newtons. But it's a term that's tossed around a lot, so don't be surprised if you hear a battery called an EMF or symbolized by epsilon. So the equivalent resistance for resistors in series is Rec equals R1 plus R2 plus R3. You just add them up. And again, it makes sense if you think of adding them up as having a longer resistor, because the length increases resistance. Series circuit characteristics. 1. The current is constant throughout the circuit. It has nowhere else to go, so it just goes through one path. 2. Individual components may use varying amounts of voltage. You have voltage drops with resistors. And 3. The total voltage used is equal to the voltage of the battery or power supply. There's also a fourth. If any part of the circuit fails, the whole circuit is interrupted. And this is the supreme disadvantage of series circuits. For example, this used to happen often, still does sometimes. When one Christmas tree light goes out, they all go out. How are these type of lights wired together? Well, they're wired in series. And if something's wired in series, if one bulb goes out, they all go out. But with parallel arrangements, this doesn't happen. If one goes out, the rest stay on. So let's talk about parallel circuits. Another way to connect a circuit is in parallel. In this arrangement, each component is connected separately in its own loop. For example, you can have two batteries and then hook up some wires to that. You have a loop with a resistor in it. Then make another loop with a resistor in it. And then you can even make a third loop with the resistor. And so we have three resistors in parallel. Now notice what we have here is we have three different paths that the current can take because it can branch off. And also if one of the loops gets interrupted, the rest stay fine. So parallel circuit characteristics. The current in the different branches can vary. That's the first one because it can branch off. 2. The total current of the circuit is the sum of the individual branches. That makes sense because they all have to add up and combine if they split up. Number 3. All branches of the circuit receive the same voltage of the battery or power supply. And number 4. A break in one loop doesn't affect the others. And this is the greatest advantage of the parallel circuit. This is also why most Christmas tree lights now are wired in parallel, and also why your household wiring is parallel. Not only so that all your appliances get the same voltage that they're designed for, but also so that if one of the appliances is turned off, you don't have an interruption to your whole household circuit. Batteries in parallel. When batteries are connected in parallel, their currents add up, but the total voltage is the same as each individual battery's voltage. So it's kind of the opposite effect when we compare it to hooking batteries up in series. And so let's say we have these C batteries here, 1.5 volts. Well, if we connect three of them in parallel, we're still getting 1.5 volts, but we will get triple the current. And so this is a good trick sometimes if you need more current but low voltage. Just hook batteries up in parallel. And that brings us to basic circuit principle number 2. Each element connected in parallel has the same voltage as the power source, but the overall current or amount of charge of the circuit is the sum of each parallel element's current or amount of charge. Here we have a parallel circuit, and notice that we have 10 ohm light bulbs just like we did in the last example. And we have two 12-volt batteries in series, so total of 24 volts, also like the last example. But in the last circuit, it was all in series, wired in series, and here it's wired in parallel. A couple quick things to point out. First of all, notice how all the bulbs are burning brightly. And they're burning more brightly than the three bulbs in series were. And that's because each of these bulbs has access to the same voltage. Each bulb has 24 volts. Instead of being dissipated or spread out over the different bulbs as they were in series, here in parallel, each bulb has access to the same voltage. Now let's just quickly prove that to ourselves here. If we use the voltmeter, we can see that it's 24 volts down there, and then if we move it up to the next bulb, it's also 24 volts, and if we move it up to the next bulb, we'll see that it's also 24 volts. Okay, and so we can definitely see the difference in brightness if we compare the parallel circuit to the series circuit of bulbs, because here all the bulbs are brighter because each one of the bulbs has access to the same 24 volts. Now another neat thing to point out too about the parallel system is that if you disconnect one of these light bulbs, the other ones are still going to work. Alright, so let's do that here. If we split this junction in the middle, notice how that middle light bulb doesn't light, but the other two, they do light. Because you do have a break in the circuit, but since each of the loops has access to the battery and a direct connection to the battery, they can still draw current. Okay, so let's replace that and reconnect the junction there. Move it up a little bit. Okay, so what we're going to do here is we're going to change the resistance of one of the bulbs. And if we change the resistance of one of the bulbs, you're going to see a difference in the brightness. Okay, so let's do the top bulb here. We're going to change it to 30, just as we did in the last example. So I changed the resistance to 30, and I got 30 ohms there. All right, now look at what happened. We have a general decrease in brightness, but specifically we see that the top bulb is less bright than the other two. All right, so if you look at the rays, look closely at the rays coming from that top bulb, you'll see that they're thinner and less intense than the rays coming out of the bottom two bulbs. Now, why is that? Well, if you think about it this way. Think of this as a water pipe circuit. If you have water flowing through, well, more of the water is going to go through where it has less resistance, where it can flow more easily. Less of the water will go through the branch of pipe that has more resistance. The same thing is true in electricity. The electrons take the paths of least resistance, and they tend not to take the paths of more resistance. Each of the bulbs has access to the same voltage. However, what's different with parallel circuits is the current. And notice that there is definitely less current. You can even see how current is less on the top branch compared to the bottom two branches. All right, now let's take the voltmeter probes away. All right, and let's see what will happen if we raise the resistance even more, just to get a better picture of this effect. And let's raise it to 100 ohms. Okay, now look at how little current flows up. Because the electrons don't want to go that way, there's more resistance. The electrons prefer to flow where there's less resistance. Capacitors in parallel. Connecting capacitors in parallel is like using a capacitor with large plates. All right, so let's look at this diagram up here in the upper left. We can see that we have three separate capacitors, but since they're close together, it's almost like we have one large capacitor. And so going back to our formula of C equals K EOA over D, we can see that capacitance increases when you have larger plate area. Connecting capacitors in parallel increases capacitance. So when capacitors are connected in parallel, the voltage across each one is the same as that of the power source. The net charge is a sum of Q1, Q2, and Q3. Resistors in parallel. If we're connecting resistors in parallel, it's just like using a thick resistor. And again, we have to refer to R equals rho L over A. If you have a big A, right, a big cross-sectional area of your resistor, or a thick resistor, well, that A is in the denominator, and so if that denominator is big, well, overall resistance gets small. And so connecting resistors in parallel actually decreases overall resistance. Each resistor in parallel has the same voltage as the power source, but the currents I1, I2, and I3 add up to the overall current I net. All right, so let's follow this current I as it starts at the battery and goes around. Well, once it hits the branches, well, it's just like water flowing through branches of pipe. The water has several different paths that it can choose, or it can, go down. And so this I net current is going to split up into three branches: I1, I2, and I3. And then I1, I2, and I3 are going to meet down here at the bottom, where I'm kind of indicating now with the mouse arrow. And at the bottom there, they're all going to meet up and produce this current of I net again. Your voltage is the same. V1, V2, and V3 are all equal to V. Right? The voltage is the same because this is a parallel configuration, but the current changes because the current has several different paths that it can take. In series circuits, the current can only go one way. There's just one path, one road it can travel. But with parallel circuits, the current can go several different ways. In any case, it's still possible to simplify this circuit by finding an equivalent resistance, Rec, to replace those individual resistors R1, R2, and R3. And the equivalent resistance is going to be less than any one of the individual resistors, precisely because the current is being spread out over 3 different branches. The electrons have more paths open to them. It's kind of like having more lanes open on a freeway. Traffic flows more smoothly. Or if you have more toll booths open as you're going through some toll booths, traffic moves more smoothly when cars have different options of where to go. Well, the same thing works in the same way with electricity. Overall resistance is less when there are more paths for the current to take. All right, now we're going to derive an expression for equivalent resistance when we're dealing with resistors in parallel. All right, we already know that V of the battery is equal to V1, is equal to V2, is equal to V3. All the voltages are the same. And we know that I net equals I1 plus I2 plus I3. And so now we can recall Ohm's law. V equals I net times Rec. And then that can be rewritten as I net equals V over Rec. And then we can replace because we have our I net, and so that's going to be V over Rec. And then we can write I1 as V1 over R1, and I2 is V2 over R2, and I3 is V3 over R3. And once again, since V equals V1 equals V2 equals V3, we can cancel all those and end up with 1 over Rec equals 1 over R1 plus 1 over R2 plus 1 over R3. And this is the formula for equivalent resistance for resistors in parallel. When you connect resistors in parallel, your equivalent resistance is going to be smaller than any one of the contributing resistances. Parallel resistor example. Calculate the total effective resistance of two 10 ohm resistors connected in parallel. So it's the same as finding the equivalent resistance. 1 over Rp or Rec equals 1 over R1 plus 1 over R2. And then we do our plugging and chugging. Fortunately, the common denominator is easy to find here. Sometimes it's not. So we have 2 over 10 ohms. And now if we're going to solve for Rp, which is the same as Rec, we have to take the reciprocal of each side of the equation. And so we have Rp equals 5 ohms. Notice that the total overall resistance is lower than either one of them individually. This is what happens when you have parallel resistors because there are multiple paths for the electrons to take, lowering their resistance. The current branches off through the different resistors, lowering the total resistance. Alright, here's a problem to try on your own. Calculate the equivalent resistance for 4 ohm resistors if they are connected in series or in parallel. Pause the video, do this on your own, and resume when you have your answer. Alright, so doing A first, we have Rec equals R1 plus R2 plus R3. And then plugging and chugging, we have 4 ohms plus 4 ohms plus 4 ohms. You could have just done 3 times 4, it's the same. And that equals 12 ohms. So that's the answer to part A. Alright, part B, the parallel arrangement. We have 1 over Rec equals 1 over R1 plus 1 over R2 plus 1 over R3. And then you do your plugging and chugging. So 1 over Rec equals 1 over 4 ohms plus 1 over 4 ohms plus 1 over 4 ohms. And that equals 3 over 4 ohms. So 1 over Rec equals 3 over 4 ohms. And then solving for Rec, multiply each side by the reciprocal, and you have Rec equals 4 ohms over 3, or simply 4/3 ohms, 1.33 ohms. If a circuit is more complex, start with combinations of resistors that are either purely in series or purely in parallel. Replace these with their equivalent resistances. As you go on, you will be able to replace more and more of them. Alright, so let's look at this somewhat complex circuit. And there's no battery, there's nothing to worry about. We just have a certain portion of a circuit where we've got some resistors. And we want to simplify. Okay, so if you would ever like to simplify a circuit like this, you just do one step at a time. Alright, so here's what we're going to do first. Let's look at this top loop here, where we have a 12 ohm resistor and a 4.0 ohm resistor. And let's simplify that, keeping in mind that those are wired in parallel. And so we recall what our equation for equivalent resistance is. And we have 1 over Rec equals 1 over 12 plus 1 over 4.0. And then we find the common denominator, and that turns out to be 12. And so 1/12 plus 1/4 is 4/12. And that makes sense because 1/4 is just 3/12. So 1/12 plus 3/12 is 4/12. And finally, Rec equals 3.0 ohms. All right, and that'll bring us to this simplified drawing. Notice that the parallel loop up there disappeared, and we just replaced it with 3.0 ohms. And now what we can see is we have this top branch here that includes a 3 ohm, two 3 ohm resistors and a 4 ohm resistor. Well, those resistors are all in series with each other. And so for that, you just add them up. So 3 plus 3 is 6 plus 4 is 10. And we end up with this simplification. And so we have 10 ohms on the top branch and 10 ohms on the bottom branch. And so we can see there's just one final step. And that final step is going to be to simplify or find the equivalent resistance for these parallel resistors. And so 1 over Rec equals 1/10 plus 1/10. And that means that 1 over Rec equals 1/5 because 2/10 is 1/5. And so Rec equals 5.0 ohms. And our final answer then is simply 5.0 ohms. All these different resistors, we had 5 in the beginning. In the upper left here we had 5. All of those have an equivalent resistance of just a 5 ohm single resistor. Now what happens if you have too many resistors in parallel? Well, it can be dangerous. Let's say you had some kind of chaotic mess like this in your house. Well, that's a fire hazard. Because if your household wiring is in parallel, you keep adding devices. This allows too much current to flow because the current branches in parallel arrangements, and this can be very dangerous. So we have fuses and circuit breakers to avoid the danger. To prevent too much current from causing a fire, fuses are designed so that they melt and therefore break the circuit before that happens. Old fuses melted to interrupt the circuit. Most homes today have circuit breakers. They don't melt, but are designed to switch off power to overloaded circuits. This has probably happened to you. If you plug in too many things or run too many things at the same time, a fuse causes the circuit to interrupt. And then you can manually reset it. So this avoids fire in the house. Alright, so in this series circuit, we want to calculate the current and electric potential difference, or voltage, for each component of the circuit shown. So we have a 5-volt battery, we have a 5 ohm resistor, and we have a 10 ohm resistor. A good first step is to simplify the circuit. And it's good to simplify the circuit because then it's much easier to work with. So circuit simplification. Because this is a series circuit, to combine the resistors and simplify the circuit, they are merely added together. And so the 5 ohm and 10 ohm added together gives you 15 ohm equivalent resistance. So we just use that simple equation of adding the resistances up. And we got 15 ohms as the equivalent resistance. So current in a series circuit. If we have the same circuit with the equivalent resistance of 15 ohms, we're going to use the voltage of the power supply and the total resistance of the circuit to find the total current flowing through the circuit. So V equals IR by Ohm's law, I equals V over R, and therefore I equals 5 volts over 15 ohms, which is 0.33 amps. Because the electron flow has nowhere else to go, this amount is also the current flowing through both resistors. I1 and I2 is that same 0.33 amps. Voltage in a series circuit. So going back to the original circuit, since we know the current flowing through each resistor, we can use Ohm's law to find the potential difference or voltage for each of those resistors. So we have V1 equals IR, and we can do our plug-in chugging. We know the I is 0.33 amps times 5 ohms, so we have 1.67 volts voltage drop through R1. And then we set up V2 equals IR and plug and chug and find that there's a 3.33 voltage drop through R2. Notice how the sum of the two voltages adds up to the power supply for the circuit. And this goes to basic circuit principle number 1 with series elements, and that is that the voltages in individual ones add up to the voltage of the power supply for the circuit. Parallel circuit. Calculate the current and electric potential difference or voltage for each component of the circuit shown. And so we have this circuit here, a 5-volt battery, and we have a 5 ohm resistor, 10 ohm resistor. Notice how this parallel circuit contains the exact same components as the series circuit we just did. They're just arranged differently. And so let's see how the currents and voltages behave differently. Voltage in a parallel circuit. Alright, so the easy part about any parallel circuit is the voltage applied to each item, because for each loop in the parallel circuit it's the same. And that's because each item has its own independent connection to the battery or power supply. Each item receives that potential. So in this case, V1 and V2 are each 5 volts. Current in a parallel circuit. Alright, so dealing with this parallel circuit, once you realize that the electric potential or voltage for each resistor is 5 volts, find the current is easy using Ohm's law, V equals IR. So I1 equals V1 over R1, and that gives us an I1 of 1 amp. So there's 1 amp going through the 5 ohm resistor. And I2 equals V2 over R2, and so we solve and find that 0.5 amps are going through the R2 resistor. So there will be an overall current of 1.5 amps. Now let's do a simplification of the circuit just for practice. So pause the video and try to find the equivalent resistance on your own and resume when you have your answer. Okay, let's go through the solution to that. We use 1 over Rp or Rec equals 1 over R1 plus 1 over R2. 1 over Rp equals 1 over 5 ohms plus 1 over 10 ohms. Get the common denominator. We have 2 over 10 ohms plus 1 over 10 ohms, and that's 3 over 10 ohms. And so finally we can solve for Rp by multiplying each side by reciprocals, and we end up with Rp equals 10/3 ohms, or 3.3 ohms. Alright, so that would be the equivalent resistance for this parallel circuit. It's 3.3 ohms. Now, we're going to make some observations. Notice the two currents add up to the same value as the total current in the circuit. This is a good way to check your work. For example, we just found that the equivalent resistance is 3.3 ohms, so the overall I equals V over R should be 5 volts over 3.3 ohms, and that's 1.5 amps. And that matches perfectly what we found before we did the circuit simplification, where we found 1 amp in one branch and 0.5 amps in another branch, for a total overall current of 1.5 amps. Ammeters and voltmeters. So an ammeter is a device for measuring current, and a voltmeter measures voltages. The current in the circuit must flow through the ammeter. Therefore, the ammeter is connected in series and should have as low a resistance as possible for the least disturbance. So here is a circuit with an ammeter connected to it, and notice that we have an ammeter connected in series between points A and B. And the reason it has to have a low resistance is because you don't want it to affect the current that you're trying to measure, and so the current should be able to go straight through it without getting dissipated at all. Alright, so whenever you have an ammeter, or if you're using a multimeter and you want to measure current instead of voltage, you have to actually disconnect the circuit, insert the meter, make it part of the circuit, and then measure the current. Now, a voltmeter measures the voltage between 2 points in the circuit. It therefore is connected in parallel. In order to minimize the effect on the circuit, it should have as large a resistance as possible. Alright, so let's say we wanted to measure the voltage drop from point C to point D. Because we know that, we have our power source, we have our circuit, but there is going to be a voltage drop as the current produced by the battery moves through the resistor R that's between point C and D. And so, since the voltage is always the same in parallel elements, we have to set the voltmeter or connect the voltmeter in parallel. Now, the thing is, though, you want very little of the current to go up into the voltmeter, just a tiny bit, not enough to really throw off your result. And that's why the voltmeter should have a high resistance, because if it has a high resistance, the current's going to resist flowing through it. And so it's not going to throw off your result. Kirchhoff's rules. Gustav Robert Kirchhoff was a 19th century German physicist who specialized in electricity and light. And Kirchhoff has kind of a neat last name. It means churchyard. So I guess one of his ancestors lived on a churchyard. More complex circuits cannot be broken down into simplified series and parallel pieces. For these circuits, Kirchhoff's rules are useful. So suppose you have something like this. Well, the reason it's complicated is because you have two different loops here, and it's kind of hard to decide or to distinguish between the series and parallel elements and how to split them up and simplify. And on top of that, you have two batteries here that are opposing each other. And so you really do need Kirchhoff's rules for circuits like this. Now, Kirchhoff's laws consist of the junction rule and the loop rule. Let's talk about each. The junction rule. The current going into a junction or intersection is equal to the current leaving the junction. So let's say we have a conducting wire that comes to a T intersection here. And let's suppose that going through that conducting wire is a current of 8 amps before it hits the intersection. Well, what the junction rule states is that part of the current comes one way and part of it comes another way, and so we have 4 amps and 4 amps. So the junction rule can be considered a restatement of conservation of charge. Charge can't be created or destroyed, and so it branches off into equal parts that add up to the overall current. Now, the loop rule says that the sum of the voltage changes for all elements in a loop must equal 0. So let's say we have this loop here. We have a 4-volt battery, and we have a resistor, 2 resistors here. Well, what you do is you add them up in order. All right, so let's say we have the 4 volts, that's positive, but then there's a voltage drop of 1 and another voltage drop of 3, and so 4 minus 1 minus 3 is 0. And then the cycle repeats itself. So the loop rule can be considered a restatement of conservation of energy. Think of the voltage as energy or an equivalent of energy. And so that voltage or that energy gets used up as it passes through each resistor until it goes to 0 and has to repeat the cycle again. And it makes sense to think of voltage as energy because a volt is defined as 1 joule per coulomb. So we are talking about joules per unit of charge. And that energy gets used up until the cycle is ready to repeat itself. Using the loop rule, let's go through some simple guidelines for using this rule. Alright, so the first one to keep in mind is that if we have a battery, we need to label the ends of the battery. The long end is the positive end, out of which the conventional current flows. Now, for the conventional current, you do have to make a guess, an educated guess at its direction, and you draw that direction into your diagram. And don't worry if you're wrong, you can correct it later. The resistor voltage is negative if you move in the same direction as the current, so that would be a voltage drop. The battery voltage is positive if you go from the negative to the positive battery terminal, which is how conventional current always goes. And finally, you create an equation using the loop rule and the path of the current. We're going to go through an example or walk through an example of this. Now, if the current is negative, that is, the value you find is negative. That just means your original direction was wrong, and so you flip it. Again, don't worry about that. You'll see how that works in the example. All right, so let's say we have this simple series circuit here that can be considered a single loop. We've got two different batteries. We also have two different resistors. And so we're going to use the loop rule to analyze this circuit. The first thing you have to do whenever you're using Kirchhoff's rules is you've got your sketch and you really have to guess at where the current goes. Now, the good news is that the guess doesn't matter that much, and that is because if you guess wrong, you're just going to get a negative answer, and then you can switch the direction you guessed. If you guess right, you'll get a positive answer, and you're fine. So it is kind of weird for students at first when they do Kirchhoff's rules because they're not used to having to guess. But when you do circuit analysis with Kirchhoff's rules, you actually have to guess. And in fact, it's your first step. All right, we're going to guess that the current goes this way, that I goes around in this counterclockwise fashion. And the reason that's a reasonable guess is because, conventional current always goes away from the positive terminal, because conventional current is the flow of positive charge. And if you look at it, well, the 6-volt battery, obviously the current's going to be going to the right, and so it's going to continue up counterclockwise over the loop, and then when it encounters the 10-volt battery, it's going to do the same thing. And so this really is the most reasonable guess we can make as to which direction the current flows. Okay, now we're going to label each element in this series circuit with a number. You don't normally need to do this. We're just doing this for the first time to kind of clarify what's going on. And we're going to set up an equation that really just expresses the loop rule. All right, because we have the loop rule that tells us that as you're going around a circuit, the algebraic sum of the voltages has to be 0, because you're going to have voltage gains and voltage drops, but there can be no net gain and no net increase in voltage. And so if we go around the loop, we're going to go around counterclockwise, we should end up with 0. And so let's use Ohm's law, V equals IR, to express the current that goes through the resistors. And so we'll set it up this way. We have V1, which is our 6-volt battery, minus IR2 for resistor number 2, plus V3, which is our 10-volt battery, minus IR4, which is resistor number 4. Now, why the minus? Because those are voltage drops. Why the positives for V1 and V3? Because those are voltage gains. Batteries are voltage pumps, so they increase voltage. Resistors bring voltage down. And so now we do our plugging and chugging. So 6 minus 5i plus 10 minus 10i equals 0. Negative 15i equals negative 16. And I equals 1.1 amps. And since that's positive, we know that our original guess for the direction of I was correct. Using Kirchhoff's rules, the variables for which you are solving are the currents through the resistors. You need as many independent equations as you have variables to solve for. And you will need both loop and junction rules. Alright, so these are pretty self-explanatory, but just to point out a little bit of, just to clarify something on number 2 here, you need as many independent equations as you have variables to solve for. Alright, so let's say that you are looking for 3 different currents because you have 3 branches. So you have I1, I2, and I3. Well, in that case, you would need 3 different equations. Or let's say you have 4 different branches, I1, I2, I3, I4. Well, you would need 4 different equations. So here's an example of Kirchhoff's laws. We have 2 different loops here. We have a top loop and a bottom loop. And on the bottom loop, there's a 6-volt battery. On the top loop, there's a 9-volt battery. And we're going to try to figure out the currents through the different branches, through the different resistors. We're going to make our guesses. So the guesses are the following, and let's see why they're reasonable. Well, I1 is reasonable because conventional current goes away from the positive terminal. I3 is reasonable for the same reason. And the only thing that's a little bit ambiguous is I2 because it, without knowing the facts and without doing the problem, it could go either way. I2 could go right and it could go left. And so here's where you can do something that you're not used to doing when solving problems, is just pick one. Pick whichever one you feel like. If you like to go right, pick right. If you like to go left, pick left. Why doesn't it matter? Because if you do the problem correctly and find that I2 is negative, that means that you have to flip the direction. If you find that I2 is positive, it means your original direction was right. So we're fine going with this guess. Now we set up our equations. I1 equals I2 plus I3. This is how we apply the junction rule. And the reason this works is because if you see, if I2 goes this way and I3 goes this way, well, then they have to meet up and form a single current I1 that goes around this way. Another way you can think about it is this. I1 comes around here, around this corner, and then it has to split off at this junction, and so when I1 splits off, it will split off into I2 and into I3. So I1 equals I2 plus I3. Now let's set up an equation for the top loop. And again, we're just using voltages here and adding the voltages to get the final sum of 0. And so the top loop that I'm talking about is this loop up here. I'm circling it now with the mouse arrow. I'm referring to this loop, the top loop. Alright, so that, if you like, the top half of this rectangle. And so if I go around counterclockwise, which is where these two currents are going, my equation would look like this. I have the 9.0 positive voltage minus 15I2, and that's because I have a 15 ohm resistor. V equals IR, so 15I2 would give me the voltage of that, or the voltage drop. And then I keep going around, go to the top, then I have minus 22I1, and it's I1 because this whole top branch here is I1, since the amount of current going out of the battery always matches the amount of current going into it. So I have minus 22I1, and that equals 0. Now I have a bottom loop equation. So the bottom loop I'm talking about is this guy down here, the bottom half of the rectangle, if you like. And again, I'm going to proceed counterclockwise because I'm starting at the battery, and so I have a positive 6.0. And then I have a positive 15I2. Now you might ask, well, why? Isn't it a voltage drop? Well, it's a voltage drop for the top loop, but it's a voltage gain for the bottom loop because, see, the I2 current is going in a way that's opposite to that counterclockwise flow. And so that would be considered a voltage gain. If I2 had been going the other way, or rather if we guessed it the other way, I2 going left, well then that left would align with the counterclockwise flow of the bottom loop, and then we would have minus 15 I2. But we're going to go with our original guess, and so we have plus 15 I2 equals 0. Alright, now it's time to solve this system of equations. So let's do the easiest one first, the bottom loop. We have 15 I2 equals negative 6.0, I2 equals negative 0.40 amps. So the negative sign means that I2 goes in the opposite direction, and what that means is that my original guess was wrong. But you don't need to worry about that yet. And when you do these problems, you're often going to guess wrong for one of the branches, but it doesn't matter because when you finish the problem, then you can just correct which ways the arrows are pointing. Alright, so we're just going to write I2 as negative 0.40 amps for now. And the reason we have to go with our original guess, even though now we know that's wrong, is because our whole system was based on that guess. So you do the system correctly, and then you just change the arrow signs as needed afterwards. Alright, so we know that I2 equals negative 0.40 amps. Now let's solve the rest of the system. Let's plug that I2 into the top loop equation to solve for I1. And so we have 9.0 minus 15 times negative 0.40 minus 22 I1 equals 0. That comes out to negative 22 I1 equals negative 15. I1 equals 0.68 amps. And finally, we can use that to substitute in for the first equation, and we have 0.68 equals negative 0.40 plus I3, and so I3 equals 1.08 amps. And so now we found all three currents using Kirchhoff's rules. We used the junction rule and the loop rule. And so we have them labeled here. I1 equals 0.68 amps. I2 equals 0.40 amps. Notice what I did there. I wrote it as positive, but changed the arrow sign because now this is the way the current actually flows, the conventional current. And finally, I3 equals 1.08 amps. Here's a working model of the circuit that we just solved. We see the ammeters are showing 0.68 amps, 0.40 amps, and 1.08 amps. Now notice something about the direction of electron flow. So these little blue spheres are representing electrons. Notice that the electrons flow in exactly the opposite direction to the conventional current. Conventional current is the direction of positive flow. Actual current is the direction of negative flow. And that's why it's directly opposite to those arrows that we just found correctly for the conventional currents. This is a problem. Using Kirchhoff's rules, find the current through every resistor of the circuit below. Now, I've done part of the work for you on this. That is the guesswork. And so you can see on the bottom right here, I've labeled I1, I2, and I3. Now, let's take a moment just to understand why it's reasonable. And then later on, you'll be better equipped to guess on your own. Alright, why is I1 reasonable? Both of these arrows down here represent I1 because it's the same current. I1's reasonable because it comes off the positive terminal of the bottom battery. I2 is reasonable because it comes off the positive terminal of the 30-volt battery, the top battery. Alright, and then I3 is reasonable because if you look at where I2 is going and where I1 is going, well, the only way that the combination of the two can go is this way. Alright, the way that I3 is labeled as going, counterclockwise. It's pretty much the only way that I3 can go. And so these are reasonable guesses. Okay, so what you want to do at this point is pause the video, try to come up with a system on your own. You don't have to solve it yet, but you should try to come up with a system on your own just to get practice. Now, one little hint about the system is the loops you're going to use. You're going to use this top loop. That's kind of intuitive. This top loop here that I'm outlining now with the mouse arrow. Okay, but your other loop that you're going to use is going to be this bottom loop, which includes part of the top loop. Okay, so just tracing out what I mean here. Tracing out what I mean this whole loop with a 40-volt battery, but including just a part of the top loop. All right, so that would be your bottom loop. And I'll trace it one more time. Trace it one more time just so you know what I'm talking about. That's your bottom loop. Okay, and you got your top loop. So try to set up three equations for the three unknowns. One equation you're going to use the junction rule for, and the other two equations you're going to use the loop rule for. Alright, so going through the solution, this is the part that you should have been able to get on your own, just coming up with the system of equations. You don't need to worry about the solution yet, because I'm going to explain that. But we have I1 plus I2 equals I3, and we can see that clearly from the junction rule. I1 comes this way, I2 goes down, and they have to meet and combine into I3. So I1 plus I2 equals I3. Now the top loop, I'm going to be going in this counterclockwise direction because that's where all the currents go. So I start with my positive 30 volts. minus 30I3, because I got my 30 ohm resistor, so minus 30I3, V equals IR, I got that, and then minus 10I2, because also there's a voltage drop at this 10 ohm resistor. So I have 30 minus 30I3 minus 10I2 equals 0. And now let's do our bottom loop equation. Alright, the bottom loop, I'm going to start down here at the battery, and I'm going to go clockwise because that's where the current goes. And so I start with 40, that's why it's positive 40, minus 10I1, voltage drop there, minus 20I1, another voltage drop there. And then remember, in the bottom loop, we're including just a portion of the top loop, right? And so that's why I have minus 30I3 also in the bottom loop. And so that all has to equal 0. Now I can simplify 40 minus 30I1 minus 30I3 equals 0. And there you have your 3 equations for 3 unknowns. Now you probably didn't go on to the solution. You may have tried it, that is to the calculation of this system. But I'm going to walk you through that because it uses some math that you may be a little rusty on or just haven't learned yet. Okay, so let's write our equations. I have I1 plus I2 equals I3, 30 minus 30I3 minus 10I2 equals 0, and 40 minus 30I1 minus 30I3 equals 0. I'm going to rewrite these in the following way. I1 plus I2 minus I3 equals 0. 0 I1 minus 10 I2 minus 30 I3 equals negative 30. Negative 30 I1 plus 0 I2 minus 30 I3 equals negative 40. Now, what was the reason for this? The reason for this is we're putting things in order because we're going to use something called a matrix. Make a 3x4 matrix, and that 3x4 matrix is going to look like this. 1, 1, negative 1, 0. Since the coefficients of the top equation are 1, 1, negative 1, and 0. Then my next row is 0, negative 10, negative 30, negative 30, because the coefficients of the second equation are 0, negative 10, negative 30, negative 30. And finally, my third row is negative 30, 0, negative 30, negative 40, because those are the coefficients of the third equation. Alright, so those of you who are taking pre-calculus now have already learned matrices. Those who took it last year learned matrices as well. If you haven't learned matrices yet, just don't worry about it because it's actually going to be really simple to do on your calculator. And I can quickly show you this in class, or some of your classmates can show you how to do it on your calculator. Because once you have this 3x4 matrix, you just do RF on the matrix to get your solution. Alright, so don't freak out if you don't know what that means if you haven't done this, because RF is just a function on your calculator, and once again you can quickly learn how to do this on your calculator when we get to class. Those in pre-calculus or who took it last year know the math behind it. If you didn't learn the math behind it yet, just really it's going to be enough to learn how to do it on your calculator for solving these problems. Okay, so we have our current I1 equals 0.47 amps, current I2 equals 0.40 amps, and I3 equals 0.87 amps. And since they're all positive, it means that all our original guesses were right. So here's a working model of the circuit we just solved. We can see the ammeters confirming what we found. 0.40 amps, 0.87 amps, and 0.47 amps. Notice how that lines up with what we just found. And also notice that the flow of electrons, just as you'd expect, is exactly opposite to the conventional current flow, which we correctly found in this example.
Here's the classwork. Please write these numbers down, and I will post them as usual as a worksheet. See you in class.